Welcome to BKW Physics. I'm Mr. McConley. And yesterday we talked about various types of energy. We went through a whole list. And one of them that I left blank was the elastic potential energy. I promised you I'd come back to it. Well, here we are. I also have realized that, talking to the students yesterday, that I did not mention the units for energy. So, to be complete here, the units for energy is joules, are joules. So energy is in units of joules. And you've already learned previous in the year that work was in units of joules. So now it makes sense from yesterday's lesson why those two things can be equal to each other. They got the same units. Alright, and if you're thinking back to chemistry and all your Q equals MC delta T's, the units for those were also joules. Alright, so it's all maybe starting to tie together for you why you can set these things equal, because they're all equivalents. But that's not really today's lesson. Today's lesson was elastic potential energy. There's many elastic objects. Some things you might think of are like rubber bands, springs, and stuff like that. But there's other objects that also act elastically under the right conditions. In fact, even a piece of metal or a meter stick is elastic. You know, if I hang the meter stick off the end of the table, you can see that the thing bounces elastically. So it's not just for things like springs and rubber bands, but that's usually where we start because it's easy to think of. So how does this equation go? The potential energy of a springy object is 1/2 kx squared. That's reference table material, where this is the potential energy in joules. This is the spring's constant. And basically what the constant means is how elastic or how springy is that particular spring. And the last thing is x is the elongation, which is going to be in meters. So the longer you stretch out an elastic object, for the most part, the more it snaps back. There's a limit to that usually, but so as this gets bigger, you're getting more potential energy. Makes sense. The problem is, how do you get the K value? Where do you pull that out of your hat? Well, yeah. In the reference tables, you'll also see that there's an equation. In this equation, F equals Kx also has that same constant in it. It also has that same x, which is elongation in it. But it has one other different thing. It has a force, like how much force in newtons are you putting on that particular spring. This one that I've written in red here is affectionately called Hooke's Law, after the guy who came up with it. And basically what it says is if you can add some newtons, some force to a spring, look at how far it stretches, you can find the K value. If you got the K value, you can back up, plug in, and figure out how much energy you got. Okay, that's how the two are tied together. In a graph format, it will be a linear relationship. Since it's a linear relationship, force, elongation, if you take the slope, it will give you the K value. Force over elongation is going to give you the K value. That's that equation rearranged. Just put a little s to indicate we're talking about springy objects. One last thing. If you take the area underneath this graph, what I've shaded in red here, if you find this area, the triangular shape there, you are finding the potential energy of the same spring. So this is the relationship between these two equations, elastic potential energy, Hooke's Law, physics.